This video is going to explain in great detail the concept of seafloor spreading. It's one of our most difficult sections in one of our most difficult chapters, and what makes it so difficult is the fact that it includes so many different concepts that are brand new to us. It includes the idea of convection and convection currents. It includes the different types of crust, both oceanic and continental. It deals with deep ocean trenches and mid-ocean ridges. There's just so many things going on in this concept of seafloor spreading that it's hard to understand in just one instruction. So I hope that you plan to watch this video a few times. If you look at this map, you can easily see where seafloor spreading begins. Here along the mid-ocean ridge, this is the mid-Atlantic ridge. There are several other mid-ocean ridges on this map. They look kind of like scars on the surface of the planet. These mid-ocean ridges are the places where the new oceanic crust is created. It's being born, so to speak. That's where the process of seafloor spreading begins. Let's take a look at this picture. Here you see the mid-ocean ridge, and this is where, from the mantle, molten material rises through this crack in the crust on the ocean floor. It hardens into rock. It pushes the existing rock away on either side of the ridge equally in both directions. So the rock that is right along the ridge is very new rock, very young rock. It is dense, but it's not nearly as dense as the rock further away from the ridge. As this rock is pushed further along the ridge, over approximately 200 million years, depending on the width of the ocean floor, the rock becomes older, further away from the mid-ocean ridge, in this area for example, and this older rock is colder because it's further away from where it was created here in the mid-ocean ridge. It's also more dense. This rock here, very close to a deep ocean trench, would be the most dense rock that exists on the ocean floor. So this dense oceanic crust may be subducted here at a deep ocean trench. This subduction happens because this crust is incredibly dense and it is older and colder than the rest of the ocean floor. Also, the continental crust here is very much less dense than the oceanic crust that it is on top of. So when this oceanic crust reaches a deep ocean trench, it will be subducted. At this point, it will melt because in this area you have tremendous friction happening. Right at this border, tremendous friction, very similar to if you rubbed your hands together really quickly, you would experience heat there. That's friction, and heat is created here. It melts this crust right here along the edge. It melts this crust into magma. From there, the magma could go back down into the lower part of the mantle and be recycled and perhaps come right back up through this mid-ocean ridge. That is a convection current, the main force that drives seafloor spreading. The other thing that can happen to this pool of magma that has been melted due to friction between the plates is it could burst through a crack in the continental crust and create a volcano like you see here. So two things that could happen to this magma as it is melted when it is subducted. Now, on the other side of our drawing, you see no continental crust over here. But let's imagine that over here were the coast of Africa. And here again, you have new crust being created at a mid-ocean ridge, and it is slowly spreading this way. Newer, younger crust here, older crust here. If this crust were to come across the coast of Africa, and there is no trench to subduct it, then this oceanic crust is literally pushing the coast of Africa along with it. No subduction is occurring. If we look at this map, you see here our mid-ocean ridge creating the crust, and if it is pushing this way, there is no deep ocean trench along the coast of Africa, no red lines in this case, and so it is literally pushing the coast of Africa away. The same thing is happening on this side of the mid-Atlantic ridge. No deep ocean trench on the east coast of North America, and so as the crust is growing from this mid-ocean ridge, it pushes North America this direction. And because of that, because there are very few deep ocean trenches here in the Atlantic Ocean, the Atlantic Ocean is expanding about as fast as your fingernails grow. On the other hand, the Pacific Ocean has quite a few deep ocean trenches. As this crust is growing in this direction, there are plenty of places in the Pacific Ocean where that crust can be recycled back into the mantle to either come up as volcanic islands, volcanoes, or go back into the mantle to come back up at another mid-ocean ridge. Even in this area, you have crust growing this direction and being subducted at this deep ocean trench. So the Pacific Ocean is actually shrinking, whereas the Atlantic Ocean is expanding. This video is intended to help you understand how the convection currents inside Earth's mantle work together to move the plates. The map that you're looking at will help you understand because it is exactly the same area as your model. We were focusing on this area in your model right here. This circle would represent the circle on top of the model that we made in class. Let's focus on that as we look at how the plates are moving. The African plate is moving in this direction. The Arabian plate is moving in this direction here. So the Red Sea, which is here in the middle, is literally parting. And all of that is due to the convection currents that are in the mantle underneath that area. So under the crust in that spot, you have a convection current going this direction and a convection current next to it going the other direction, which literally drives these two plates apart. They're resting on the soft asthenosphere, and they are pieces of the lithosphere, and they are being pulled apart because of the convection currents that are running in this direction. And of course, those are going in a complete circle. Now, the same thing can happen in a different direction because it is the direction that the plates move, or excuse me, the direction that the convection currents move that determines the direction that the plates move. Back on this map, the Eurasian plate is moving this direction, and again, this plate is still moving in that direction, and so we end up being able to see mountains here being created because the convection currents are forcing these two plates to come together. We can see that happening on the left side of this map here. Here's a convection current going in this direction. The one next to it is going in that direction. So here this piece of crust and this piece of crust are coming together. And when that happens, it pushes up mountains. And that again is happening because the convection current is moving in this direction. I encourage you to watch this video again and again until you understand how the direction of the convection currents determines the direction that the plates move. And remember, those plates are sitting on that soft asthenosphere. The plates are sitting on this asthenosphere, and that is what makes them able to move. They're kind of sitting on a river of silly putty that's moving around very slowly, and it does affect their movement.
Convection currents aren't the only thing that moves Earth's plates. They're not the only force in play here. Another force besides these convection currents here is the ridge push. At the mid-ocean ridge, material rises in the mantle, and that creates this mid-ocean ridge, which, as you know, is an elevated chain of mountains and volcanoes and the bottom of the ocean floor. These are higher in elevation than the rest of the ocean. And because of that, gravity pulls the surrounding rocks down and away from the mid ocean ridge in opposite directions. It's moving the lithosphere away from the ridge. That's ridge push. Now, along with ridge push, the convection currents underneath in the asthenosphere create basal drag. And that happens because of these convections in the asthenosphere circulating at the top of the convection current here. They drag the plate in the direction the convection current is moving. So on this side, the convection current is going up and it drags the plate in this direction. That's basal drag. A final force that's involved in moving the plates is slab pull, and that happens in a subduction zone here in a deep ocean trench. There's another one over here. The slab pull occurs because this plate at this point, the oceanic plate, is older, colder, and denser than anything else around it. And as it is being subducted, it is literally being pulled into the crust or into the asthenosphere. And as it does that, it is dragging the rest of the plate with it. And it's believed that the slab pull is actually the more significant force involved in moving Earth's plates at the moment.